So welcome to the third installment of the reinforcement learning seminars of ICARL. Today we are honored to have Haitham with us, who is the head of the reinforcement learning team in Huawei, honor lecturer in UCL, and who is done a lot of autonomous work in statistical machine learning, Bayesian optimization, and reinforcement learning, and is going to talk about all the subjects today. So without any further introduction,
thank you. All right. Yeah, thanks a lot. I'm really very happy to be here. This is my first talk after COVID in person, actually. So it's definitely exciting. At the beginning, I wanted to talk all about Bayesian optimization because I found this field to be giving us some very exciting real-world applications. But then we came to realize that, or I came to realize that this is more of an RL seminar. So what I've done is I split the talk in two. So I'll cater to the BO people and then I'll cater to the RL people. So yeah, let's get started. I think Clicker isn't working.
Yeah.
All right, now it's working. Okay, so before I go ahead with some of the technical stuff we're doing, I just want to give you an overview on who we are and what we're trying to do, right? So we have a mandate. So I come from Huawei, so I lead the reinforcement learning team. We are in London, in King's Cross. We have an office, which is just in front of Google. And my team now is about 25 to 30 people. It just varies depending on interns in and out and so on. What we are tasked with is to try to make deployable machine learning-based decision-making in real-world applications so that we can aid humans in complex scenarios. And we work on a lot of real-world applications, and I really mean real-world. So we have real data, we work on real-world, we have deployed solutions to those problems. So we're working a lot on self-driving car problems. We're working a lot on AI for medicine problems, which we started actually maybe towards the end of last year. I'm going to talk a bit more about that today. We have been working on AI for compilers. So we were trying to optimize compilers using machine learning. And actually, we tried reinforcement learning here, and then we found that BO is better. So we went back to BO. We also worked with the 5G networks a lot. And I have some collaborations set up with like Professor Jan Peters from TU Darmstadt, where we work a lot on robotics. We have access to real robots and we do some stuff. So the team architecture itself is like this. So it's really called the reinforcement learning team, but it's weird to be called the reinforcement learning team from my point of view. So the team has three sub-teams. So we have a Bayesian optimization team, which is maybe relatively the bigger team among those three. Then we have the safe and robust RL team, and then we have the multi-agent team. So the RL team in Huawei London is actually split into these three things. And the reason why we split them in this way is that because we realized that the intersection of those topics is actually very interesting, some of the real world applications. So of course, those are not silos by any means. In fact, we have a lot of collaboration happening across the board, right? And those are just some of the papers that we have published over the past 1.5 years to 2 years. I don't have much time to describe all of them, but I just would like to say that if anybody here is interested in BO, would like to do an internship, or is looking for a position, interested in safe RL or multi-agent RL, please let me know. We have a lot of open positions, and I'm very happy to talk to you in more details. We also have won some notable awards over the past year. So we got like the Best Paper Award at ICARL, as well as the finalist for Best Paper Awards at IRIS and the AMAS. And at the same time, we have won the NeurIPS 2020 competition on Bayesian optimization. So that's our team up there. We were competing against a lot of other teams. We created an algorithm which we called HEBO, Heteroscedastic Evolutionary BO, which was really less of a novelty thing, more of taking the best tricks from everywhere, getting them to work. And then that seemed to be a very good thing to do. We also open source our research. So everything I'm going to talk about is already open source. So you can go and find the code. It's right there. And also we contribute to Ray tuners, for example, which is, I'm sure some of you know about Ray, and that's our algorithm in there. Okay, so let's start with the first part. I'm going to discuss first Bayesian optimization. So people who don't like it, don't sleep, just try to follow me. And then we're going to jump to RL later, all right? Right, so what is the problem that we're going to focus on today in the Bayesian optimization side of things? We're going to be interested in maximizing some function f of x subject to some constraints with respect to that optimization variable x. So we have an optimization variable x, which we would like to find, and we have a function f, which we can query. but we can't know its closed form equation. So it's a black box in that sense. So for example, I will give you examples on what a black box would look like or would be. But the idea is that you cannot differentiate through this black box. It's very hard to do your differentiation through that black box. And we also have those constraints. And the constraints are at the same time black box constraints. So I don't know the form of the constraints, right? And they are very expensive to compute. So I can query them. I can ask the question, at this x, what's the function value? What is the constraint value, right? But one query of this would take a very long time to give me back a number. Right? So it's not like RL in a sense, because you don't have the ease of simulators with you, right? So you can't just say, okay, I'm going to do 100 trillion steps of things. I cannot do that, right? And it's just very expensive to deal with those things. So you have to be smarter about, how we work around this problem, right? So as I said, it's a black box, right? So we don't know its closed form equation. Maybe it's not even differentiable. We don't know, right? And it's very expensive to compute. Now, what we would like to have from our solution is we would like to have a data-driven solution. So we would like to have an agent, right? Some sort of an agent that will give you a point. You will try that point, right? Then you will get a function value back and a constraint back, right? And then based on that, you would like to get the feedback and then try to improve, find the new point you would like to try. We would like it to be data efficient, right? So I want a reduction in number of queries to find the optimum, right? So because I can't afford to wait years to get hundreds and thousands of trials, right? So I would like to find a solution that will be able to solve this problem as efficiently as possible in terms of number of queries or sample complexity. And we would like a solver that goes beyond the gradients because, gradients, the function itself, it's a black box. It might not be differentiable, so I really don't know what to do with it. And at the same time, we would like a solution that produces a feasible X in the constraint set that is given for me. So now, okay, I just gave you an example, a problem, and then you might be like, okay, why? Why is this of any interest? Why is this interesting? So I would like to elaborate more I would like to elaborate more why we should bother about solving those types of problems. And I would like to convince you that some of the most exciting problems today are actually of this form. It's a black box F, which is very complex to evaluate, and it's a constraint, which is also very complex to evaluate, and it's really expensive. So to do that, I'm going to talk about antibody design, right? So what is that? And let's go through that. Right. So imagine an antigen, comes into your body. So say COVID, just pops into your body. Now, what you would like to do is we would like to design an antibody for COVID, right? To, hook to COVID as soon as possible and very fast without having 100 trillion trials, right? Now, it's very hard to do simulations, right? So it's very hard to write down those simulations. So in fact, the simulator in our case is the real world, right? It is me creating something, giving it to a chemist, manufacturing it, giving me back a number, right? So what are we going to create? So we're going to deal with antibodies. What are antibodies? They're just this Y-shaped structure here, right? And on the top or in the tip of this Y-shaped structure, there are 6 loops. We call them L1, L2, H1, H2, H3, and L1, L2, L3. Now, those loops are called the CDR regions or the complementarity determining region. What is so good about those loops is they allow for a lot of variability and specificity to target antigens. So, for example, if you are able to design them successfully, you can actually find a antibody, for a specific target antigen. And now the question is, what is the good CDR given an antigen popped into your body? That's kind of the question we would like to solve. So let's dig a bit deeper into what are those CDRs, right? So CDRs are nothing but chemical compounds that actually combine together in order to form proteins. So they are made of the same structure that proteins are made of, right? So if you know, a protein is typically made of a set of amino acids, where an amino acid has an amino group and a carboxyl group, and then they come together. As they come together, they combine together, and that forms for you a polypeptide chain, giving you a protein, right? No need to really dig into all the chemistry. I'm not an expert in the chemistry either. We have doctors on board who taught me all this stuff, right? But I'm just saying that keep in mind that all you really need to do is just to design this sequence of amino acids, right? So how bonding happens? Well, when you get 2 amino acids, the carboxyl group and the amino group will come together. They will emit a water, and then they will form a chain, right? Now that chain, as it forms, right, that will be your protein, right? So now CDRs are nothing but those chains, right? So they're made of those chains, and the length of those chains can go from 50 to 4,000 amino acids stacked in a sequence next to each other, right? So now, one property we need to keep in mind, which I think is really important, is that the order by which you stack amino acid matters a lot, right? So for example, here, if I stack for you amino acid tyrosine, glycine, phenylamine, leucine, right? Then you'll get an opiate, right? So that's like a pain modulation drug. But now if I flip the order, so I just say, I'm gonna go backwards, I'm gonna go leucine, phenylamine, glycine, tyrosine, then you would realize that this has no pain modulation effect. So the order by which you stack your antibodies, right, this actually affects the functionality or the property the antibody will have. Right. So so what is our goal, right? So now the whole idea is very simple in this way, right? So given an antigen that enters to my body, okay, I would like to find a good CDR sequence that will bind to that antigen, right? So I would like to have a CDR sequence, which is like, I'm asking the question in this space of, let's say, 4,000 chain of amino acids, each being 1 out of 20 or 22 possible combinations. What's the optimal combination that will allow me to bind to the antigen that enters to my body, right? So the binding energy is kind of a determination of how good or bad, right, your sequence of amino acids was, right? And now your goal is to minimize the binding energy with respect to the CDR sequence, right? So I would like to find the optimal CDR sequence that will minimize the binding energy of binding the CDR sequence, which is the tip of my antibody, if you recall, with the antigen. Yes?
Question I'd like to relate to the optimization. So is it the case that changing, for example, one peptide to the wrong chain is to binding energy?
Yes, and you will see. Yes, yes. So the answer is yes, and that's why when we use the GP, the best kernels we used were not the simplest kernels we had. We actually used like a protein BERT kernel. I'll come to that. Yeah, the answer is yes, and yes, two amino acid sequences, right, could have very close distance in the amino acids, but can have very different binding energies. So it's really a kind of a non-smooth looking behavior, right? Right. So yeah. So any other questions so far? Okay. So all I'm trying to say in this problem is that I would like you to find for me the sequence of amino acids, right, that bind to my target antigen. Right. Now, please notice there are also constraints on my problem. Where do those constraints come from? Well, not every sequence of amino acids that you create is actually something we can manufacture in the real world. There are amino acids which are stable, more stable than other amino acid sequences, and there are certain constraints you don't want to have inside your chain. For example, your hydrophobicity should be within certain ranges. But maybe the easiest one to explain is that if you had an amino acid sequence with 5 repetition of amino acids or more, that's very hard to synthesize, right? So therefore, there's a constraint set that there are allowed amino acid sequences, there are unallowed amino acid sequences. And now, so therefore, our goal is to actually solve this problem, right, and be feasible with respect to my constraints. Now, of course, the search space is combinatorial, so it's really huge, right? So that's why I say it's like finding a needle in a haystack, but the haystack is bigger than the universe. It depends on the size of your amino acid chain, right? Now, so this is our problem formulation. Now, please notice that the binding energy and the constraint satisfaction are very, very slow to compute processes, right? If you would like to have accurate models, those are really, really slow to compute. So, for example, this could be a chemist giving you back a binding affinity, right? Or it could be something like a very ugly, complicated physics simulator, like a PyMol or something that's actually dealing with this, right? So those two are very hard to compute, right? Like it's very expensive to compute. And additionally, one thing to note, please notice that if you would like to go differentiable around this problem, that's a problem for you, right? Because these are discrete entities, right? Like what is the gradient of binding with respect to the R sequence? We don't know that, right? So this is also not necessarily very differentiable thing. Right. So okay, so now I'm hoping with this problem, I convinced you that the problem setting is actually important, that we wanted to consider before. And there are many other problems that could be written like this, right? So think about, for example, maybe the closest to your hearts is tuning hyperparameters of neural networks, right? That is a similar problem to this. But to me, I found BO to be a very broad thing, and not just to tune hyperparameters. In fact, a lot of decision-making can be written as BO, right? So, okay, the way we're going to solve this is in a really simple way. What we're going to have is we're going to have an agent, and that agent talks to my black box, right? And the agent, when it talks to my black box, the way it talks to my black box, it says, okay, here's x1, which is my trial of my solution. The black box returns for you a value f of x1 and a constraint value, right? And then with time, the agent accumulates this data in its knowledge database. And then over time, it should start proposing new xi points, which are closer and closer to the optimum, right? But now please notice, if you look at this, you would say, oh, but this is RL, right? Like, I need a policy picks an action, right? I get a reward and so on. Yes, but remember, if you want to do RL, you have hundreds at most trials that you can do, okay? So yeah, so I want to improve the guess of the optimum while being data efficient. The way we do that, we're going to have a two-step solution. The first step solution is we're going to learn a Bayesian model. And the second step solution is we're going to maximize our acquisition. The Bayesian model we use is Mark's favorite, which is a Gaussian process. And I will just say a word or two on how we're changing Gaussian processes. And when it comes to maximizing the acquisitions, the goal of this step is to trade off exploration versus exploitation. In fact, to ask the question, where should I go next, right? So given my model, that's my posterior belief on what the function behaves. What should I try next, right? So that's what this step is trying to do. Now, acquisition functions are split into myopic versus non-myopic ones. So myopic ones just look, they are greedy, and maybe those are the most famous ones you hear about. And there are also like knowledge gradients or entropy search ones and so on, but those are very hard to scale. So they don't necessarily scale very well in dimensions. So we do a lot of research on this. I will just say a word or two on this. Unfortunately, I wanted to dig deeper into this, but I also didn't want to bore you with all the BO. So we have 3 research directions on BO. So we're trying to do more scalable models. So we're trying to, sorry, but we're trying to replace the GPs now. And we are trying to have better optimizers for acquisition functions. And we also create a lot of nice libraries. So we had a lot of outcomes around this. So for example, this was a JMLR. We had some MLJ accepted and JR as well recently and so on. Right. So let me just tell you a bottleneck or two, which we found from our experience about BO. Maybe this would be opening an avenue of discussion / research. We found that training the GP is a pain, honestly. No, seriously, I fell in love with GPs about maybe, let's say, 1.5 years ago, right? But we found that the training of the GPs is very complicated, and it's actually very slow. Really slow, right? So we tried with GPUs, we tried with variational GPs. Things are way slower than neural network is, right? They definitely give me the advantage of uncertainty quantification, right? Which is what I need to explore in my BO, right? But there's still a pain. So what we recently have done is actually, there has been a new paper by Frank Huta, which created something called Bayesian transformers, right? And what is interesting is that they managed to show that the Bayesian transformer kind of follows in its uncertainty, AGP, in their experiments. And it's really nice the way they trained it. So they trained it on a lot of GPs offline, right? So random GPs they generated, they trained it offline, right? And then given that, they then took it to the BO step and just started doing inference. And then they showed that, or not BO in their case, but to predictions, they showed that they can do that. And that was interesting. So we're using it, but we're actually improving it with some additional constraints. This so far is much faster than the GP, and it seems to be able to handle heteroscedasticity really, really well, and non-stationarity really, really well, because it can give us multimodal output distributions. And that's something pretty cool. So if you're interested in BO but you don't like GPs, yeah, we can accommodate for that as well. Yeah. All right. Right. So yeah. So we have applied this framework into our antibody example that I just gave you. Right. So remember, I wanted to have a model which was my GP, whereby I modeled my function using a GP. So my input were these different sets of CDRs, and then I tried to get the posterior of the function conditioned on those CDRs, and then I maximized the acquisition. Now it's important to note that in a combinatorial space. Yes. Go ahead.
Sorry, just a side question. Do you incorporate, like, if there's quite a little data set behind it, incorporate that into your file?
No, we don't. So this is a very good point. We could do that, right? We could do that. However, we wanted to show that starting from scratch, BO is a good thing to do in those problems. And apart from one kernel, which was the prot-BERT kernel, because that had a pre-trained BERT, because we tried to pre-train or to jointly train the BERT with the margin of the GP. That was a nightmare, right? So we went back to a pre-trained BERT. But other kernels we used, they were actually all from scratch, right? Yeah. So just I wanted to say one more thing here. When you are maximizing an acquisition in a combinatorial space, please keep in mind that your GP will locally be maybe very good, yeah, but globally it will be really not that great because the combinatorial space is humongous, and the kernel you use for a combinatorial GP is typically like a kernel, like a Hamming distance kernel, which says if the two strings match at one stage, right, they mean they're close. If they don't, they're far, right? So that's why we actually do local search. So we search within a local trust region in the combinatorial space rather than over the whole combinatorial space, which gives me better and better solutions around the best solution I found so far, right? Right, and then this is our overall architecture. So we had our antigen coming from here. We had the CDR, which is like this actually set of strings proposed by BO. It goes into those like PyMol, which is, or HADOC, which are some of the simulators, or Absolute. You get back a binding energy and the development score, and then you solve the constraint BO problem as I described just now in here, and then you loop over and repeat, right? That's the whole method. Now, this is a very interesting thing. So those are the results. So let's talk about those results in a bit more details. On top of every panel, you see a name, right? So that is the name of the antigen, which we got from the protein database bank, right? So that's the PDB, which is a very big data set of proteins, and it has antigens, right? So one ADQA, one FBX, whatever, those are just different antigens, right? On the x-axis here, I show you the number of designs, so the number of CDRs we tried. On the y-axis here, I show you the binding energy. So remember, we want to minimize, so lower is better, right? Now, you also see three horizontal lines, right? So you see this horizontal line, and that horizontal line. So those are different classes of binding affinities, right? Or different classes of binding energies. So people deem the blue line up there, for example, as a good binder, right? Like it's a good binder. Then they deem the red one as a, like, I think we call it super binder. Yeah, super binder. And then they deem the purple one as like super plus binder, which is like a, you know, the lower you go in energy, the more is specific to this antigen. Now, we tried different types of algorithms here. So, for example, AntBO is our method, right? SSK means that the kernel we used was a substring kernel between the two amino acids. Combo, which is a very famous combinatorial optimization method. Turbo, which is also a very famous Bayesian optimization method. Genetic algorithms, and HIBO, which is our previous method that won this NeurIPS thing I told you about. And then we also tried AntBO prot-BERT, right? So what we have done there is we used protein BERT, which is like a language model designed for proteins, in order to warp the space of the amino acids into Euclidean space. And then in the latent space, we just stuck a GP on top of that, right? So we tried to do that jointly to train the protein BERT, but that didn't work. So we had a pre-trained protein BERT, and then on top of that, we had the GP. And then what you can see is always BO will give you a better performance. But what I found very interesting is that you can get very good binders in 35 trials in most of the cases. You can get super plus binders in about 100 and something trials. But 35 trials are good because that's the limit that the real world can put on you when you actually want to create things in the real world. Like this is kind of a lab limit in a sense. So getting lower is better, 35 is not a bad thing. But I also wanted to show you here that I also told you I want to be feasible with respect to my set of constraints. So I also want to show you here that all of our methods are actually feasible with respect to the set of the constraints we have defined. So acidity, hydrophobicity, etc. And to be honest with you, we also compared this to RL. I don't show the RL results here, but RL didn't do that great on this problem. But it was the simplest RL, so we tried to improve it. Okay, that ends the BO part. Sorry, I didn't talk more about it, but I really want to talk a bit more about the RL. I'd like to take any questions you might have on this part. Yes?
I have a whole bunch of questions, but I'll try and keep it short. So the first question was, you said that you used the protein for example. Right, so this is pre-trained on just predicting amino acids in the middle from a big data set of amino acids that code for protein.
Yeah, exactly. Good point. So, so this has been pre-trained on continuing proteins, essentially, right? So what you get is you get a sequence of amino acid, you mask it, right, and then you continue. You try to continue the protein. But that's interesting because now your latent space, if you do that, should learn what it means to continue a certain protein.
Yeah, there's no information pre-training about what binds to what.
There's no information, right? The only and that's yes, so correct. And what we did actually fine-tune that on antibody data, right? Because proteins are something, antibodies are something else. And therefore, we needed to fine-tune it a bit on the protein data. Now, as you see, it didn't work that well in our experiments. I think it's the green line. It still did better than genetic algorithms, maybe Hebo sometimes and combo, but it's not great. The reason for that is because we think we didn't train it enough on the antibody data, right? So now what we're trying to do is we actually the problem is that you don't also have a lot of antibody data. So what we try to do now is we are doing something called declutter, which is a pre-training step of the protein BERT based on unsupervised antibody data, right? And then we hope that that would help it. Yes. Yeah. And what's nice is that based on the binding energy that we get, you could actually do a self-supervised learning step for the protein BERT because now it can cluster good binders in its latent space. Oh, I just evaluated for now, right?
But where you get binding from for the generated antibody?
Yeah, I could just stick it in here in like one of those. Yeah. In one of the. For now, we use a very low fidelity one, right? But that opens a very interesting problem of how can you do this contrastive learning with so little data, right? And that's why we thought that if you constrain the protein BERT with the marginal of the GP, that would be something good. But yeah, we couldn't get it to work.
So 2 more questions.
Yeah.
Do you have in the slide where you compare the result?
Yeah.
Do you have a comparison to some kind of predictor that doesn't use the uncertainty of the Gaussian process? So specifically, I'm trying to get a sense for how important the Gaussian process.
Yeah.
Or was it just helpful?
So we use genetic algorithm and we use random.
It's a search algorithm, right? So
yeah.
If you do something like expected improvement, but without the uncertainty of the Gaussian process.
So just take the mean or something.
Yeah.
I don't think we tried that. No, I don't think we tried that. We just ran different. Yeah, no, it does not. Yeah.
You could model it, but without uncertainty, and then that might tell you how the neural network might.
Yeah, no, that is a good point. Actually, we could try that, but that gives us we can get a hint on that from our RL results, which I don't show because there it didn't do great, right? And we were using like things like deterministic policies and stuff. So we tried with both, but yeah, I mean, we could have a dedicated experiment on this. We didn't do that here. Yeah.
And a final question. So how does this problem relate to the kind of sequence to structure problem that AlphaFold kind of addresses?
Yeah, that's a good point. So it's a sub part of this. So let me just tell you the pipeline, right? So the pipeline is this. Right, so we have this simulator here, right? So let's call it absolute, or let's call it PyMol, or some physics, right? And then you will have your CDR sequence here, right? Okay, now, typically what happens here is that you need to convert this to a 3D structure. And then you would pass here the antigen, which also has a 3D structure. Right? And then what will happen here is that they will try to dock them on top of each other in the simulator in all possible pockets and return for you a set of energy values, right? So that's what's happening, right? So you could, in fact, that's what we're trying to do now. You could put AlphaFold in here instead of what this model was using, right?
Okay, yeah, super cool. So AlphaFold would only make, using AlphaFold would only make your work better and more relevant.
I hope so. Yes, I agree with you. But I also have to be clear, when we talk to biologists about this, they don't think AlphaFold is great for antibody predictions. It's good for large, long proteins and good, not long proteins, but kind of smaller molecules, but it's not great for antibodies, right? However, then AlphaFold multimer came out, which is trying to address similar problem. What we're trying to do now is we're trying to fine tune it on antibody data. But it's still not clear, to be honest, what will happen here. But we're already sending this paper to Cell to see what happens, right? So let's see. Yeah. Yes.
I have a question about the specificity of the line examples. Is it usually the case that one sequence will line very explicitly to one and not the?
No. Yeah. Can I use the internet? Okay. Yeah. I mean, no. I just wanted to show you that we have a diversity plot, but maybe you can see it later. I don't know. Okay. Well, no, you don't have to take my word. All right. Oops. Right. So yeah, this is loading. 1 second. So I will show you just a diversity plot that, in fact, we don't necessarily just converge to get true optimum, but to a distribution over those. And I just would like to note that this work also has doctors on board, which is good, because I'm not an expert in this, and they know what we're doing more than we do. Right. So I just wanted to show you here. So those are the different kernels you see, right? Those are the different kernels, so protein BERT, SSK, combo, HIBO, etc. Right, and those are the sets of good binders that we have found, right? The clutter depending on the color, right? So as you see, it's not like finding the one of them, but it's actually finding a class of possible good binders. Yeah. All right. Sorry for that. Okay. How much time is left? Okay, great. Yeah. Okay. Any other questions? Okay, so now let's go to the RL side of things. Right, so we're doing a lot of work on reinforcement learning, ranging from non-station reinforcement learning with model-based reinforcement learning. But maybe the most excited work I am about is this new method we created for safe reinforcement learning, because it generated for us a plug-and-play solution. And I literally mean a plug-and-play. It's actually 10 lines of code in OpenAI Gym environment, and then you get safety almost surely, right? So I just want to tell you how we did it and what it's all about. So yeah, so let's start with an MDP. So everybody knows an MDP, right? So you have a state space, you have an action space, you have a transition model, you have a cost model, and you have a discount factor, right? So the state space is where the agent is in, the action, what actions we can take, how we transition from a state to a successor state is given by P. The cost is kind of the task goal, what we want to solve. Gamma is just a discount factor. There are so many reasons for having gamma. I like to say it's just we use it so we don't diverge in our inference series. Some people go ahead and tell you don't look ahead, look ahead. I don't buy that. This is just a discount factor, so we don't diverge, essentially. All right. Now, what's our goal? So the goal in reinforcement learning is that we would like to find a policy that just minimizes the cost or maximizes the reward. I'm just writing it in terms of cost here because I define C, which is negative reward. So what I would like to do is I would like to minimize my total discounted cost. So I have a time horizon, and then I would like to find that policy pi, which on expectation under my distribution and under the policy if it's stochastic, to minimize my total discounted cost. Okay. Now, in order to deal with safety, one of the nicest frameworks that handle safety, which is from my point of view very principled, is constraint MDPs. So constraint MDPs are MDPs, but add two components to MDPs to reflect constraints or safety we're interested in. So this is what a constraint MDP looks like, right? So a constraint MDP is just an MDP which has the standard components, state, action, transition, cost, and discount factor. But we have two additional components here. The first component is a safety constraint cost, and that is a cost function like C, but it's just another cost function specifying the safety we'd like to have. And gamma, which is another discount factor, but it's kind of a cost-related discount factor. Our goal now, we have two chunks in it. So we have the same chunks as before, which is just trying to minimize my total discounted cost, right? But now I have a constraint, and I would like to be feasible with respect to my constraint. So my constraint says that I have a budget D of failures I could make, right? And I would like, on average, that my total expected cost to be less than D, right? So I'd like this to be positive, right? So in other words, I would like to finish this problem by either taking off, exploiting all my budget D, or just having some remaining budget D with respect to D. So now this set of policies is smaller than the original set in the sense that now we would like to find a policy that minimizes cost, but also kind of minimizes my safety violation given my budget, okay? And any questions on this? All right. Now, the way you would typically solve a constraint MDP is you would formalize, so you would do the same thing you would do with any constraint optimization problem, right? So you would have an optimization problem which is minimizing the cost subject to constraints. Then what we typically do is we form the Lagrangian of that, right? Where we transform that into a min-max problem, right? So we write a relaxed, unconstrained version, and then we can say, instead of minimizing the cost subject to the constraint, I'm just gonna have a Lagrangian or a constraint-free formulation, which tries to minimize over pi, maximize over the Lagrange multiplier lambda, my cost with the lambda multiplier subtracted with the constraint, right? So that's very common Lagrangian formulation. And then if you actually solve this problem, you will realize that there is a very simple solution, because all it will say is that the optimal solution to this problem with respect to lambda is going to be 0 if you are satisfying your constraints. Otherwise, you're just going to be infinity, right? So what does that mean? It simply says, as long as you still have a budget to exploit, then what you're going to do is you're going to focus on the task cost, right? But once you start getting off and like violating your constraints, then we have to be careful, and I'm going to penalize you a lot so that you start caring more for your constraint set, right? So that's what these conditions mean. If D is greater than that, it means you still have a budget left, so please focus on the cost. If D is less than that, you're out of budget, so let's penalize you. Be careful about the cost. Okay. And maybe this is the most widely used safe RL solution. If you look at STRPO, SPPO, all those things that are coming from everywhere, even people who gave a CVAR conditioning on the constraint, that's how actually they solve the problem. They write a Lagrange multiplier, then they prove convergence using 2-time scale techniques, and then they go from there. However, there are problems with this formulation. So first of all, given that your policy, if you just consider a policy which is conditioned on the state, it's really not clear if you can get a Bellman-like update for this policy, right? And intuitively, when you are taking an action with respect to unsafe region, it would be really important to have a feature of your state telling you, are you safe or not safe, or am I gonna expect in the next place to transition to something unsafe, right? So really, it would be nice if we can get a policy that is conditioned on the state, but also some safety features that will take into account safety when we are making our decisions, right? Now, directly, of course, because before you could say, I'm taking it indirectly, but I would like something to directly, explicitly depend on those safety features. And it's important that we can prove convergence of our methods, right? It's really important that we will show that we get to a feasible set which is safe, right? So it would be really nice if the updates we make on this safety thing is actually abiding by a Bellman equation, right? It would be really nice to show that, to prove that, for us to guarantee that our algorithms reach somewhere useful. that's beyond, applying it and making sure it works. Would like to see that as well. Right. So then the big question that is being asked here is, what is this safety feature we should add to my state, right? What is it that I should augment my state space with, right, in order to guarantee what I was just talking about, right? So what is it? Should it be a ZT value? Should it be gamma ZT? Should it be D minus gamma ZT? What is it, right? What is that safety feature I would like to add that will guarantee good behaving things for me? Right, so I would like to have some properties, right? First, I would like to have Markovian transitions, because if I have Markovian transitions of my augmented state of the original state and safety, then it's good because Bellman equations will hold, and that's nice. I would like, to policies to take the safety information in their choice of actions. And the most thing I would really love to have is I want to have a general enough method. Like, I don't want to create one algorithm to solve safety in RF, right? I just want something generic that you take the algorithm you love, any algorithm you like, right? And just plug this simple thing I'm going to do on top of it. And then I guarantee for you that you have almost sure safety, right? So almost sure means safety with probability 1, right? That's what I would like to get. So if you think about it, really, it's like it should be a property of the OpenAI gym environment rather than a property of the agent, right? Because if you do that in some way, then it doesn't matter what your policy is, what your algorithm is, apart from some cosmetic changes, maybe growing your dimensionality by 1 because I went in my state by 1 or 2, whatever, it should work, right? So what's that thing? Right, so that thing is something actually interesting, because it turns out that if you look at this, let's look at the safety budget, right? So let's look at the safety budget. If you realize that's D, right, minus the sum of the costs so far, right? So that's like the safety budget I have left, right? So this is all the mistakes I've done so far, right, weighted by my gamma, and I'm taking D from that, right? D is my safety budget, okay? Let's call that WT minus 1. Now, if I define a variable, right, that is this safety budget divided by gamma Z to the power T, right? So if I define a variable, which is simply this change of the budget divided by the discount factor of the constraint, right? Then I can show that the evolution of this variable lambda is nothing but the old lambda, subtracting from it the cost that you encountered xt at, divided by a constant, which is gamma Z. Now, why is this nice? Because that's a Markovian thing, right? So if you realize everything T will give me T plus 1, right? So you have xt at, lambda T gives me lambda T plus 1. So everything is Markovian, right? So if I can actually track this in my implementation, right, then I'll just grow my state variable by 1, putting this thing in there, right? And then I could track my safety, right? That's what's happening. Right, so that's the first thing. So we can actually do that. And upon doing that, we now have a state space, which is the original state space augmented by this lambda variable. Please notice this lambda is not the Lagrangian multiplier. I just overloaded notation by mistake. This is eta, something else, right? Okay. Now, of course, as we augment the state, we also need to shape the reward, right, or shape the cost. Yeah, we can't just keep the cost as it was before, because that will just focus on the task and it will ignore the safety information. So I'm just going to do a simple reward shaping of my cost, whereby I'm going to define my cost to be just the task cost, right, if my variable is positive, if my lambda T is positive, meaning that if there is budget still to exploit, then let's just focus on the task, right? If there's a budget mistakes to exploit, let's just focus on the task. Otherwise, let's be highly punished, right? And now what you realize is that you get this nice problem formulation here. Okay, with an expectation missing, by the way. But that problem now is constraint free, right? It has no constraints in it. And if you look at this, you can use any algorithm you like to implement, right? Like if you look at this, you can put SAC here, you can put PPO, you can put TIPO, you can put reinforce, you can put anything you want, right? As long as you're able to track this lambda T, right? So that takes me to what we created, or what we called safety augmented MDPs, or SATE MDPs. The Sate MDPs, they take a constraint MDP, which we described before, and then they augment the state space by this lambda variable we just described. They augment the transition model by the old transition model and this new Markovian transition model we found, right? Which is just what we found here, right? So we augment the state space with this lambda, and this is the transition model of lambda, right? And then we reshape the cost based on the this state variable we augmented. And in our implementation, we didn't put infinity here. We just put a very high number just to be more computationally friendly. But we prove in the paper what happens as n goes to infinity, that you actually recover everything nicely. And then, of course, our goal is to solve this problem, which you can use any algorithm you desire. So in reality, and I'm not kidding you, I'm impressed by this personally, that you can guarantee almost sure safety if you take OpenAI Gym and you just change those functions, this. Like literally, like if you just take that, you can guarantee everything I said. So it's really agnostic in a sense to the agent we would like to have. And that's our environment. We're just going to augment the state. We're going to augment the cost, right? So our step function will be overridden to include a safety step in it, which will track my lambda, right? And then, of course, my reset function as well, because I want to reset my augmented state, not just my old state. Okay.
Guarantee almost surely safe. Does that depend on the actual reinforcement learning algorithm working as it should work, right? Because you basically won't know the satisfaction of safety compared to whatever reinforcement learning algorithm you're actually running.
Yeah, no, so you're absolutely right. However, I just want to make an admission here. When RL people do proofs, they rarely talk about neural nets. They rarely talk about, high dimensional continuous things, right? So we actually go back to standard MDPs, right, with discrete states and discrete actions, and then we do proofs from that perspective, right? Now, that being said, I just want to make sure that there is work on that, but we didn't use it here. We just focus on the discrete, like our proof is based on discrete states and discrete actions.
So basically, if you had a method for which that guaranteed that the reinforcement would be solved, and there are such methods that have such guarantees for certain environments.
For maybe even simplistic environments, yes, then you will get almost sure certainty. Yeah. Yeah, but also, so what it means is that you just need to be able to recover the optimal policy, right? Which means you need to be able to recover the optimal value function, etc. And now from that place on, how safe you get depends on the algorithm you use. If the algorithm can never converge to the optimal policy, then you'll never have safety, right? So that is super true. Yeah, I said something I should maybe just smoothen a bit. Not all RL people do these assumptions, but most do, but there is a lot of work recently happening on linear function approximators, and also there is one paper I think 1 year ago about BQNs, but they grew the network to infinity. It wasn't really more like a neural network anymore. So so there is work happening, but for now, for us, our guarantees are like the same way everybody else does guarantees, by assuming you can at the end find the optimal solution. Yes.
So if the D is 0, if your computation will be like safety budget is 0 at the beginning, you don't actually need that something, right? If you just augment the reward function, it should work.
Yeah, so I should tell you that lambda 0 in our case is D, right? So we start with the D budget and we decrease it over time, right? But we don't typically start with the 0 budget and increase it over. Actually, you can start from, I think one experiment did that. We start from 0 budget and then increase it over time. That also should work, yes. But to be clear, this will not necessarily guarantee safety during learning, right? It will guarantee final safe policy, right? So the safe policy you will get at the end, it's safe with respect to those constraints. But while it didn't do the budget mistakes so over time. Yes.
Kind of like application, but it's like how do you formulate like safe constraint?
So this is very interesting. When we were working with self-driving cars, we actually got the constraints that look like this from the experts of engineers that are working on the car itself. So they told us things they don't like to see. For example, they don't want the jerk of the car to accelerate a lot because that's going to be like a very bumpy ride. Also, you don't want to get very close beyond a certain region to obstacles around you or to other cars near you, right? So this needs domain experts, right? But to be honest, maybe this is something I would like to say. Machine learning people should be less arrogant. What I mean by that is we don't know everything. It's really important to talk to domain experts and to learn from them what their problem really is, because not all of my models will work on their problems. So it turns out we had a lot of discussions for us to be able to do that. And there's no one model fits all, to be honest. Yeah. Yes.
Yeah, I wanted to ask because I'm just concerned about the point you said when you go above budget to increase utilization like to infinity. If our experience when the domain is complex and you have a high utilization, the policy that is more dominant is that the is too afraid to do anything. For instance, when I was working with card remove when I was making too hard utilization.
Yeah. So good point. Scheduling this D is very important, right? So if in reading the paper, I think that we proposed or played with different possible schedules, right, or different scheduling techniques, right? And yes, you are right. But as I will show you in a second in the results, maybe not very complex domains, but we will solve the task and be safe, right? So it's not like we will guarantee reward is high as well. In here actually, yeah. But yeah, any other questions? Right. So okay, so those are the domains we played with, right? So we had the simple domains, which are the pendulum and the double pendulum, right? So those are the tasks. This is the unsafe region in red. So you have to control your problem, kind of avoiding that unsafe region. Similarly, we had the PR2 robot and we had a safety gym environment. So we now have extra safety gym environments, right? Tasks, but they are there. And because I told you it's plug and play and you can use any algorithm you like, so I have to prove that for you. And that's why we worked with model-free algorithms and model-based algorithms, right? We just didn't stick to one algorithm. We tried the RPO, PPO, SAX of Factor Critic. We tried PETS, which is like an MPC-based method for model-based RL. It's very similar to Pilco in a sense, but it just uses ensemble of neural networks to give you your distribution rather than a Gaussian process. And model-based policy optimization, which is another policy model-based technique that does that. Here we had 3 flavors, right? So we had the vanilla flavor, so we don't consider the constraints. We had the Saté flavor, which is what I described with this state augmentation. And you also have the Lagrangian flavor, which is, you just add lambda and then you solve the min-max problem. And right, so here are some of the results. So let's look on those results. First of all, let's look into this PPO curve right there. This is a very weird way to present the results, but we couldn't think of a better way to present them. But the line you have here, this dotted line, is the safety budget that you don't want to, go over. And the first bar here is the safety cost. And the second part here is the reward, right? So the lower the safety cost, the better. The higher the reward, the better, right? It's a very confusing plot. But the idea is that you would like this green guy, to go down, and you would like this, well, it should be orange, but it's too small, so you see it here, orange, to go up, right? And because we would like our cost to be under the budget, so you would like those green-looking things to, be under the budget. So, okay, very confusing plot, right? I know, but we didn't find a better way for now. So we need the green to go down, we need the orange to go up, and the line is the safety budget. So we want the green to go down below the safety budget, right? Because we don't want to avoid the safety budget. So here you will see that the Saté method, which is this guy here, right there, this guy right there, this is the cost distribution. You will see that that's always under the safety budget, which we had 1 in this case. And the reward for that is high. In other words, it has solved the task, right? So we normalize the rewards 1. Of course, like the higher the better, but I think at that value, we consider the task to be solved. So you see that that's in Pendulum. You see that using soft actor critic on Pendulum again. So that's PPO, that's soft actor critic, and that's the RPO, right? Again, we also showed that this is true for the model-based algorithms. So that's MPPO, that's PETS. You see the same behavior here. So you will see that the Saté is actually lower than the budget. It actually solved the task almost as good as vanilla. Maybe we lost a bit of performance, and of course the cost is below my budget. Similarly for pets, here maybe the loss of performance is a bit more apparent than before. So here, if you compare this to this, you will see that our performance is a little bit lower. And I just show you additional experiments here. So Reacher is this robot task, and then the gym, the safety card gym is also this task. Here we show vanilla, Saté, Lagrangian, and CPO. And again, what it's nice to see in Saté, for example, is that the cost, which is this green bar, is always below the budget. However, Lagrangian is not that safe. If you see it, it violates the budget. And finally, we did some ablation studies. And those ablation studies, for example, we removed the state augmentation, we removed the cost shaping, and then we can clearly see that as you do cost shaping and state augmentation, you get better and better performance. Okay, I was just told we have 2 minutes left. So this is my last slide. I would like to leave you with those 3 statements. So machine learning is much broader than deep learning. I'm engaging a lot on Twitter nowadays, and you can't imagine how many people think deep learning is machine learning. It's not. It's just a tool in the machine learning workshop. Data efficiency, you can get it, but you have to use good probabilistic thinking. That's what we were trying to do with the BO. That's what Mark does a lot better than us, maybe. And the safety can be made plug and play if you augment the states in a good way. So thank you so much, and I'm happy to take any further questions.
Just if you go back to the benchmark slide.
Yeah.
So you kind of mentioned a baseline all the way at the start where you could add like the safety cost to the reward to discourage unsafe behavior. Is there a benchmark that is similar to that?
Yeah. So the Lagrangian one here is really all it's doing is that it's taking your cost, right, and then it's subtracting from it. So, or in our case, it's adding to it some say unsafety or some safety cost, right?
For fixed constant multiplier.
Well, the point is that we update the Lagrange multiplier because we solve them in max, right? So yeah. So I mean, if you do it by gradients.
So that is trying to do that with the formulation as a constraint.
So there are 2 baselines here, right? So that's the
even dumber, right? Like just add the safety cost to the reward and try and express the safety penalty.
No, I mean the point is that no, I agree with you. I don't think that idea is dumb per se, because I think it's what the Lagrangian is doing with the fixed lambda, you know. Because all that would be is like you fix lambda, let's say, to 0.1 or something, you know, and then you will take your cost and subtract from it 0.1 the safety cost, right? And that would amount to what you had in mind. The problem with that is that that's okay, but then you have to tune your lambda a lot because, you know, your lambda will vary a lot depending on where you are in the region, how much the cost is, and so on. So yeah, so in a sense they are close to each other. Just to add, CPO is another baseline, which actually is solving the constraint problem itself, right? So it's trying to do projections and constraint sets and so on, right? So that's another baseline. Yeah.
So we're gonna stop here with visual seminar. So I guess that I don't have 2 minutes if he wants to finish, but for those of you who want to go, thank you for coming. The next seminar will be on the 26th of May about open-ended RL with Roberta Reneo from Meta AI. Thank you for coming. Hope to see you back.